Hey math fans, last time we went ahead and established and proved something called the inclusion-exclusion principle, which allowed us to find probabilities of arbitrary unions. This episode we're just going to start right off with an example of this. So it says suppose n students have n identical raincoats which are all hung on the same coat rack during class. After class, each student selects a raincoat at random, being unable to tell it apart from the others. Presumably all their names are stitched into their own raincoats so they could tell at the end whose raincoat was whose. But we want to know the probability that at least one raincoat ends up with its original owner. Okay, so to solve this problem, we're going to go ahead and set up a couple of events. So we're going to suppose that a sub k is the event where the kth person selects the kth raincoat. We're going to assume that both the people and the raincoats can be enumerated. So maybe the third person selects the third raincoat, which is just their raincoat. And we're also going to let A be the event that at least one person selects their raincoat. At least one person selects their raincoat. And the phrasing at least one indicates that this is going to be a union, because at least one is the same as 1 or 2 or 3 or all the way up to or n. So we can also say A is really the same thing as the union over all the k's from 1 to n, these a sub k's. Okay, so we want the probability of A. And the probability of A is the probability of this arbitrary union, which last time, according to the inclusion-exclusion principle, is going to be equal to p sub 1 minus p sub 2 plus p sub 3, and so on, until our last term is p sub n. Okay, but let me just kind of remind you what this notation means. Okay, so we'll say that p sub m, do it in this color, remember that p sub m is going to be the sum of all the intersection of m tuple events. Okay, so what that means is we're going to go ahead and set up m events. And those m events, we're not just going to enumerate 1 through m, okay, because it's not necessarily the first event, the second event, so on. It's just m of them. Okay, so in order to properly talk about that, we're going to go ahead and say something like, k sub 1, k sub 2, and so on, all the way until k sub m. Those are going to be our m events, where k sub 1 could be 17, for all that you know. But as long as we have m of them, then we're going to sum over all such events where these m are going to be between 1 and n of the probability of the intersection of a sub k1, intersect a sub k2, intersect all the way until we're intersecting a sub k sub m. Okay, so that's what we're trying to find. Well, the first step really is to see if we can find this probability. So we need to really look at the intersection of all of these events and see if we can find that. Okay. So our first step is going to be to try to find this. Well, that's not actually going to be so bad. So I'm going to kind of see if we can do it off to the side. So remember that the probability of something by definition is just the number of ways that something can occur divided by the total number of outcomes. So we're going to make use of that. What is the total, what's the number of ways that this can happen? Well, first we need to figure out exactly what that even is. Remember, the event a sub this is the event that the a sub k sub 1th person, which could be the 7th person, the 10th person, whatever k sub 1 is, but this person selects their raincoat, and that person selects their raincoat, and this person selects their raincoat. Okay, so what I'm going to do is to figure that out, we're going to kind of maybe do a little aside here. Realize that to find this, we're going to go ahead and take all of the possible n individuals and break it up into m of them, and then the remaining n minus m. We're going to take a look at how many people or how many opportunities people have to select raincoats. Okay, so we're going to go ahead and start by considering the first m people. Okay, k sub 1, k sub 2, and so on. Okay, so maybe this is the first individual, which we've designated k sub 1. How many different choices do they have for their raincoat? Well, according to this, by definition, this is the event where they select their raincoat. There's only one choice because they only have the one raincoat. So likewise, the second person is also going to have one raincoat to select, and so on all the way until the mth person likewise has just one raincoat. Pretty boring so far. Then it gets a little more interesting because then we have n minus m individuals. Okay, so let me just kind of summarize what happens. So these m people selected their raincoat. And beyond that, who knows, right? The remaining n minus m people, they could select their raincoat or they could not. This intersection only says that m people have to select it, any m. Okay, so then we're going to have more individuals select their raincoat. And we're going to start off with the m plus first person. How many opportunities do they have? Well, they have a total of n minus m because the m people already selected their raincoat. So there are then n minus m remaining raincoats. Okay, so that means that the m plus second person is going to have n minus m minus 1 raincoats to select from, all the way until we get to the last person, and they only have the one option. Okay, so remember, according to, I think it was Theorem 1.2, that we multiply all of these together, and the ones don't really interest us, and we have this expression, which is a factorial that starts from n minus m and descends until we multiply by 1. Okay, so we have n minus m remaining people. And again, they could select their own raincoat or they could not. It doesn't really matter, but we're only concerned with, at a minimum, these people have to. Okay, so this is going to equal n minus m factorial, is what we've determined. Okay. Now, how many different total ways are there to select the raincoat? Okay, so what does n equal? Let's think about it for a second. We're essentially sampling without replacement. And remember, when you sample without replacement, that means that the first person is going to have n options, the second person is going to have n minus 1 options, so on and so forth until the nth person only has one option. So that means that capital N is just n factorial. Okay, so now given this and this, we can form a probability. So if we go back up, we just kind of answered this question. Okay, so let's see. So we have that. The probability of a sub k1 intersect with a sub k2 intersect with a sub km is given by n minus m factorial, all divided by n factorial. Okay, so now in order to find p sub m, we have to sum over all possibilities of k sub 1 through k sub m being between 1 and n. Okay, so what this is saying is that the probability for m individuals to select their raincoat is this. Now we have to find out how many different ways there are for m people to be arranged from the n possible students in the classroom. Okay, so when we're summing this up, where the k sub 1 all the way through k sub m, when that's going to be between 1 and n, we're asking how many different ways are there for m students to be selected from the total of n, right? So this is going to be equal to the same result that we got before, so I'll just copy that for us. It's still going to be n minus m factorial over m factorial times the number of ways to order or select m students from n total. Okay, because remember, this classroom might look something like this. And maybe if m is, say, 3, I could arrange those 3 students so that maybe these guys pick up their own raincoat, maybe these guys pick up their own raincoat. So how many different ways are there for m students out of the n to select their own raincoats? Well, if you're thinking about the binomial coefficient, if you're thinking of n choose m, you'd be correct. That's exactly what it is. Or another way of phrasing this is how many different subpopulations are there consisting of m individuals. Okay. So that means that our answer of what is p sub m, which remember was the sum probability a sub k1 intersect all the way intersect a sub km is equal to n minus m factorial over m factorial times this binomial coefficient, which remember by definition was n factorial divided by, okay, and I made a mistake. This should be n. Did I make that mistake anywhere else? Yeah, I did. Darn. Okay, did I make that anywhere else? Okay, no, I didn't. Apologies there. That should be n. Okay. So yes, the binomial coefficient is going to end up being m factorial times n minus m factorial. And the amazing part about this problem is that cancels and that cancels, and we get a final answer of 1 over m factorial. So p sub m is just simply 1 over m factorial. I'll go ahead and box this, but this isn't our final answer. But this is a great step. Remember that the probability of A, since A was an arbitrary union, is equal to p sub 1 minus p sub 2 plus p sub 3 and so on, plus or minus p sub n, and we now have formulas for all the p sub m components. Okay, so this is going to equal 1 over 1 factorial minus 1 over 2 factorial plus 1 over 3 factorial, and so on, till we're adding or subtracting the 1 over n factorial. Okay, so now we're going to spend some time and figure out what this is. I mean, really, we're done, right? If you want to call this a day and say that that's our answer, fine. But it doesn't really help us because we don't even have a decimal expansion. I argue that we can actually approximate this to a reasonable degree and get a number out of this, or a percentage, a probability. And it's going to rely on the Taylor series expansion of one of our favorite friends, the exponential function. Okay, so let's just remind ourselves what the Taylor series for the exponential function looks like. So remember that e to the x is equal to the sum from k equals 0 to infinity of x to the k divided by k factorial. Okay. And also recall the formula that we just derived for the probability of our event A looks like that. Okay, how can we write that as a sum? Well, it's going to be the sum from k equals 1 to n of, let's see, you might think 1 divided by k factorial, but that's not quite true because they alternate. So I actually argue that this is going to be -1 to the, we'll say k plus 1 divided by k factorial. Okay, so you can verify this. In fact, I encourage you to pause the video and just verify that this works for various values of k. When k equals 1, this is going to be even, so it's going to be -1 squared, which is a positive. So that matches the fact that that's a positive term, and then from there it's just going to alternate signs. So let's see if we can come up with a relationship here. Well, these are pretty different looking so far. What are the differences here? Well, for starters, this starts from k equals 0, and this starts at k equals 1. Well, that's not the biggest issue because I can always just write this as, I can write e to the x, and I can just plug in k equals 0 and I get, x to the 0 over 0 factorial plus the sum from k equals 1 to infinity of x to the k over k factorial. Right? And this term is just 1 because anything, or x to the 0, assuming x isn't 0, is 1 divided by convention, 0 factorial is 1. Okay, so it's 1 over 1, which is just 1. There we go. First problem solved. Now the next problem is, what is the value of x? Well, an excellent candidate is -1. Right? Just look at it. We have something to the power of something k. Here we have something to the power of something k. So I would let x equal -1. Okay, so we have e to the -1, if we just go ahead and plug that in, is going to equal 1 plus the sum from k equals 1 to infinity of -1 to the k over k factorial. Now what are the differences? Well, the difference is, number one, this has a +1. Okay, so I can just go ahead and subtract that over. Okay, so I get that the sum from k equals 1 to infinity of -1 to the k over k factorial, that is equal to e to the -1 minus 1. Okay, and now we're almost done because a couple of differences. The first difference is that this is to the k plus 1 power, and this is to the kth power. Okay, so how do I rectify that? Well, I just need an extra -1 here. So I'm just going to multiply both sides by a -1. So times -1 times -1 times -1 until I get 1 minus e to the -1 is equal to the sum. Let me write it a little lower. 1 minus e to the -1 is equal to the sum from k equals 1 to infinity of -1 to the k plus 1 all over k factorial. And now we're essentially done. There's only one more difference. Can you spot what the difference is? Well, the difference is this. Here we're summing only from k equals 1 to n. Here we're summing from k equals 1 to infinity. Okay? But honestly, I argue that for large enough n, this is precisely just the probability of A. And actually, the values of n don't even have to be that large. And you can manually compute, and I think there's going to be a problem on the problem set where you actually compute what this is for various values, and you'll see that it's pretty close to the actual answer. And 1 minus e to the -1 is going to be 0.632. So a little over 63% chance that one person, at least one person, is going to select their raincoat. And I think that's plausible. Okay. Now, I wanted to just kind of introduce this and talk about the fact that up until now, we've always assumed that we've had a finite number of events. Okay, but the unions and intersections can be of an infinite family of sets. But we just have to be very, very careful when we talk about probabilities. Because if we do the inclusion-exclusion principle for an infinite number of events, p sub 1 minus p sub 2 plus p sub 3 minus p sub 4, and so on forever, that's a problem if you're adding probabilities that where the limit doesn't go to 0. Right, because that's going to be a sequence that clearly goes to infinity, which means the sum, the infinite sum, is going to diverge. Okay, so let's kind of talk about some notation. We'll set up and then prove the Borel-Cantelli lemma in the next episode. Okay. So in the case of infinitely many events that are mutually exclusive, okay, so suppose that we have, a family of a sub k's, where now k is going to just be allowed to roam over all natural numbers. So we have a sub 1, a sub 2, and so on forever. We have the following relationship. We have that the probability of the infinite union from k equals 1 to infinity of a sub k is going to equal the infinite sum from k equals 1 to infinity, the probability of a sub k. Okay? So clearly, we want the sum to converge. Now we're going to kind of talk about what it means. We're going to kind of talk about what this probability means. We're going to prove an important theorem. Okay, so theorem 2.3 is basically going to say if a sub 1, well, if a sub 1, a sub 2, and just so on and so forth. Okay, I guess I should stick with notation here. So if we'll say a sub k, where k is in the natural numbers, is an infinite family of events. Really, you can think of these as sets, such that a sub 1 is fully included in a sub 2, which is fully included in, a sub 3, and so on. You have essentially a nested family of events. Okay, so you have a sub 1, and then bigger than that is a sub 2, bigger than that, and so on. Okay, then we have that the probability of this infinite union it's infinite, so that's infinity, is actually just going to be the limit. It's going to be the limit as n approaches infinity of the probability of a sub n. Okay, so what is this saying? It's saying that really this is the same thing as looking at the probabilities as n approaches infinity. And if the limit exists, then that's the probability of this union. Okay, so you don't necessarily have to do this, right? In Calc 2, this would be the same thing as defining S sub n as a partial sum, right? As the partial sum from k equals 1 to n of maybe your sequence a sub k. And then the whole sum is just the limit as n approaches infinity of the S sub n terms. It's kind of a similar notion. Okay, so the last thing that we'll do is let's go ahead and prove this. Okay. And this proof is actually going to be very important because it's going to give us kind of a very important skill in forcing sets to be mutually exclusive. And it's something that in measure theory we call disjointification. That sounds like a big word, but it's actually a really fun word. Okay, so we're gonna use a process called disjointification. Okay, so what does that word mean? Disjointification is the process of turning a family of sets into another family of sets that is completely mutually exclusive. How does that help us? Well, that helps us because then we can just use this. And then we can really look at them as partial sums, and then it's pretty easy. Okay, so I'll say then use star, or I'll go ahead and denote this as star. So that's the idea of the proof. How on earth do we do that? Well, from the family a sub k, where k is allowed to just be in the natural numbers, we're going to go ahead and form a new set, a new family of sets b sub k. As follows. All right, so pay attention. B sub 1 is just going to equal a sub 1. It's pretty standard. And also remember that in this situation, we have that a sub 1 is completely contained inside a sub 2 and so on and so forth. Okay, to form b sub 2, that is going to be a sub 2, but a sub 2 contains a sub 1, and we want it to be mutually exclusive. So we are going to subtract off a sub 1. And then so far, b sub 1 and b sub 2 are mutually exclusive. I need you to check that for me really quickly. They have nothing in common. B sub 1 is a sub 1. b sub 2 is a sub 2 and not a sub 1. Nothing in common. Okay, so what would b sub 3 equal? Well, this is kind of not the best notation, but it's essentially a sub 3 minus, we'll say maybe, well, yeah, we'll say minus a sub 1 union a sub 2. Right? So we are not including either a sub 1 or a sub 2. So we are excluding a sub 1 and we're excluding a sub 2 by De Morgan's. Okay, so another way that we can phrase that, well, is exactly like that. And we can go on. Maybe we'll just do one more. So what is b sub 4 going to equal? Well, it's going to be a sub 4, and then we are excluding the rest. So we are excluding a sub 1, a sub 2, and a sub 3. And this is going to continue, so on and so forth, until we have b sub for an arbitrary n, and that's going to be a sub n excluding the union from k equals 1 to n minus 1, right? Because we want a sub n. We just don't want everything up to a sub n to be included. Okay, now that does a couple of things for us. So from this process, we have that b sub k's are all mutually exclusive. So that's the first thing that we notice. The second thing that we notice, you might think, oh, well, you did something weird. The b sub k's have nothing to do with the a sub k's because you just completely messed that up. Actually, no, I didn't, because the union from k equals 1 to infinity of the a sub k's is equal to the infinite union of the b sub k's. And in this theorem, that is exactly what we care about. Okay, the last thing that we notice is that the union from k equals 1 to just n of the b sub k's, what's that going to equal? Well, that's going to precisely be a sub n. Why? Because remember that essentially b sub k is going to be precisely a sub n minus a bunch of stuff. Okay, but if we're taking the union of all of these, we're saying that it could either be a sub 1 or a sub 2, not a sub 1, or a sub 3. And since they're all contained within each other, that is just going to be whatever set that you're on. Okay, so that's what we have. And now we can actually form a probability. So we have that the probability, let's just kind of scroll up and remind ourselves what we're trying to prove here. We're trying to prove that this probability is really a limit of probability of a sub n's. Okay, so let's go ahead and start with the probability from k equals 1 to infinity of a sub k and see what we get. I'm actually going to use a different color. Okay, so probability k equals 1 to infinity of a sub k. Well, remember, according to number 2, so by 2, this is equal to the probability of the union from k equals 1 to infinity of the b sub k's. And now, since the b sub k's are mutually exclusive, this is equal to by star to just be the infinite sum from k equals 1 to infinity of the probability of all of the b sub k's. Okay, but now since we have an infinite sum, we can go ahead and write this as the limit. We can write it as the limit of the partial sums as n goes to infinity of the partial sums of this. Okay, well, the partial sums are just going to be summing from k equals 1 to n of the probability of the b sub k's. Okay, so this is really just, taking the limit of partial sums, which you're more than welcome to do. Okay. And now we know that this is going to equal, what is this going to equal? It's going to equal the limit as n approaches infinity. Well, what is this? Well, this sum, I can go ahead and pull the probability out since they're mutually exclusive. And I can say that this is equal to the probability of the union from k equals 1 to infinity of the b sub k's. Okay, and that's going to be by step 2 again. I'm just going backwards. Okay, and now I'm going to go backwards kind of a final time. Actually, that's by star. Yeah, so that's by star. So now I'm going to go backwards one final time and say that by number 3, sorry, this should be from k equals 1 to just n. That's just to n. And then by step number 3, this is going to be the limit as n approaches infinity of the probability of a sub n. Okay. So again, really, if you want to sum up from k equals 1 to infinity of all these infinite events that could be mutually exclusive, if you can find a probability for just a sub n, you can find that, then you can just take the limit as n approaches infinity. But remember, that relies solely on the fact that one event is contained in another event. Okay, so in the next episode, we're going to look at some interesting applications of this, and then to end off the chapter, prove the first of the Borel-Cantelli lemmas. Okay, see you there. Hope you have a great rest of your day.